All right, and here is our last installment. So we have predicted the products for combustion reactions, we have done single replacement, and here is our final example for double replacement. All of the same steps and rules apply, so we're just going to jump right in here. First step is classifying. Now, I've already told you it's double replacement, but let's make sure we understand why. If I zoom in here to my reactants, I've got Na3PO4, definitely a compound. I see a metal bonded with a polyatomic ion. Then I've got KOH, also a compound. I also see a metal potassium bonded with one of my polyatomic ions, hydroxide. I know, based on this, two compounds that are going to end up switching partners is my double replacement reaction. All right, now the next part, classifying done, is write my products. As a reminder, these are both ionic compounds. When they switch partners, they're still going to be ionic. When I do that, I have to re-crisscross those oxidation numbers. And remember that when I'm switching them, like replaces like. So I cannot put two positive ions together or two negative ions because those are just going to repel each other. So it's important that when I start, I come over here. As a reminder, my metals, which are listed first, so sodium and potassium, when I look those up on the periodic table, sodium has a +1 charge, and so does potassium. All right, then I notice I don't have nonmetals, but I do have polyatomic ions. I've got phosphate and hydroxide. I know those because I memorized them in my last unit like I was supposed to. All right, phosphate, if I look it up in the back of my periodic table, has a -3 oxidation number. Hydroxide has a -1. So it makes sense here that I will flip my two metals. Sodium and potassium will switch partners so that the ionic attraction is still there. All right, what will that look like once they switch partners? Let's try it. All right, I'm going to rewrite sodium and potassium in the same spot. Right, so sodium stays here, potassium stays here, and then I'll flip-flop those endings. You could do it the reverse way as well, as long as, again, you have a cation bonded with an anion in the end. So OH ends up with sodium, and PO4 ends up with potassium. Note that I did bring the subscript of 4 over, mostly because it's part of that polyatomic ion. The sodium, I did not bring the 3 because that's not part of a polyatomic ion. Now that I'm over here, I have to make sure these formulas are written correctly. So sodium, I noted earlier, was +1. Hydroxide was -1. So if I crisscross, those cancel out. Perfect. On the KPO4, my potassium has a +1 charge. Phosphate has a -3. So if I flip-flop here, I have to have K3PO4. Okay. So I have officially and accurately written the products of my double replacement reaction. Next step is to balance. All right, I notice here I've got 3 sodiums on my reactant side, so I'm going to put a 3 in front of sodium hydroxide. That makes 3 hydroxides. I'm going to come back over here and put 3 in front of potassium hydroxide, and I just happen to have 3 potassium in my final product over here. I have now followed the law of conservation. I have balanced my reaction. And the last part here is writing those chemical names. I'm just going to review one of them. For example, let's zoom into K3PO4. This is an ionic substance made of a cation and an anion. So I'm going to name the metal, which is potassium. All right. The metals, remember, are always written first, the positive ion. Then I know that there's more than one element left, right? Because I have a capital P and a capital O, which is a really clear indicator that's a polyatomic ion. Polyatomic ions are found on the back of my periodic table. When I turn that over, we just name the polyatomic ion. This is phosphate. Right? You should still be able to do that and have retained those skills to chemically name substances. And that is an example of predicting the products for a double replacement reaction.